Thank you very much. And we have one more speaker before the break. Chifan Zhang on ResolverFuzz, which I think you gave a preview a few minutes ago. So, the floor is yours.
Thank you, everyone. So this is Chifan Zhang again. I'm a PhD student from University of California, Irvine. So today, finally I present my work, which is called ResolverFuzz. It is automated discovery of DNS resolver vulnerability with query response fuzzing. I'm very honored to collaborate with my lab mates, Xue Zongbai, and the previous works authors, Xiang Li, and Professor Haixing Duan, and Professor Li Qi from Tsinghua University, and Professor Zhou Li, which is my PhD advisor. So first, still about DNS. So DNS, we all know about that. So it is a tool to translate the human-friendly domains into IP addresses, which is machine-friendly. So for example, if you query uci.edu, so we'll get this IP address. So this is the simple example of how DNS is working. So it is a security guarantee of multiple applications. So domain names are widely registered, so it is very fundamental, it is very important. So for DNS resolution, it is also recursive and iterative process, and there are many roles, forwarders, recursive resolvers, and authoritative servers. So also DNS is very complicated, so we did a survey till the year of 2020, we have over 100 RFCs, and there are many use cases, such as web browsing email, which is widely used, and also for nowadays, for security aspect, we have zero trust network. They have some RFCs about that, and also we have autonomous driving vehicle. It's very surprising, but we also have RFC about this use case. So also we have many implementations. As far as we know, there are more than 20 widely used software or programming libraries on the market. And also, it is unfortunately very fragmented service ecosystem. We have millions of NAM servers, open resolvers, and local resolvers and forwarders. So they are spread out in the world, and they have different kind of softwares. Even this self-implement some software. So it's a very, very complicated work. So we also, it's very often to see the DNS failures and attacks, and it's always very tedious to track down and fix them. So we always have this problem, like we have timeouts, we have bad certificates, we have bad APIs, and we have mysterious errors. So it is all about DNS costs. Yes, it is. You want to take the photo? Have we finished? Finished? Okay. So then we have an idea, like, could we find those vulnerabilities automatically? Is there any possibility? So if we go to automatic bug detection, there are two ways. One is like randomized way, it's fuzzy. One is like Duane mentioned, not Duane, the one guy just asked me before about the formal verification way. So there are two ways. So now we chose fuzzing. So fuzzing is some kind of very random or very simple, I should not say that, but very simple technology to get on with this example, for example. So if you have a binary called test B and you just check help, and you say this is the input is a 32-bit integer. So you write a very easy fuzzing shell, so which means like you just randomly input those 32 bits into like integers, and finally you find someone crash this kind of test me binary, and then you got it. So this seems a very stupid, very simple idea, but it works very well for on very much many protocols and implementations. So nowadays, so let's get into the let's say this more comprehensive or more advanced fuzzing techniques, which is called coverage-based gray box fuzzing. So by coverage-based is more like for the program, you can just do some kind of labeling. And by executing the program, you will know the data, the control flow of this program, and finally you can calculate how many codes are inside this kind of program is executed. So this is a very good parameter to guide you for further randomization. And the gray box means like it is not completely a black box. You can see the logics or something you can compile with some labels, as I mentioned before, to guide this kind of fuzzing process. So one of a very famous tool is American Fuzzing Loop, which is a tool developed by Google. So what is challenges for ResolverFuzz? So the challenge one is DS bugs. They have three, they have many kinds, like cache poisoning, denial of service, access, validations. But there is one problem, fuzzing. These problems are not crash-based problems, which means if this vulnerability is triggered, it will not crash. It just returns you like a fake results, or it just do not respond to anything. So, but fuzzing is mainly focused on crash-based bugs. So how could we, so there is another problem. So we want to find which part is vulnerable, because there are non-crash bugs, and we should have something to focus. So we check the vulnerabilities that has been identified via CVEs, and we focus on those frequently vulnerable spots. So we do this kind of CVEs in a comprehensive study. So we manually analyzed 423 CVEs from 1999 to 2023 last year. So we found 291 CVEs and about 6 DNS softwares. And we found a lot of them. Actually, a lot of them is non-crash based bugs, and we can categorize them to 3 categories. One is cache poisoning, another is resource consumption, and we have other bugs. Yeah. So the second challenge is how should we like implement the stateful fuzzing? Because standard fuzzing, it is just like there's one input, and this input, when it's executed, it's gone. It's completed. But for DNS, it is stateful, because if you query one thing and there are some responses back, and there are something in the cache, and if there is another one comes in, there is another cache, so it will like interfere with each other, and also they have a time factor, which means that if there is a timeout or something, they will also lead to different query results, and also it involves multi-party. We can conclude like simplifying into 3 parties. One is clients, one is resolvers, one is the authority server, always a name server. So it is more complicated than standard fuzzing. And also we do we consider how could we do this stateless fuzzing for DNS? The answer is definitely no. We have 2 examples of CVEs. One is response without query, so this is this kind of CVE. But we also have the query without response. So this is like 2 kinds of stuff. So if you want to give away response, then how could you find that part of the problem? If you like throw away the query, how could you find the client part of the problem? So this is so you cannot like give away anything, and also you need to coordinate with the query and response during the fuzzing process. Otherwise, it's easy, very easy for DNS resolvers to reject them. And the challenge 3 is the DNS is very, we say, fragmented. So it is implemented in many systems and in many programming languages. So this finally is you cannot easily grab and use some kind of famous tools like AFL, because they are C and C++ based. And also for the code coverage problem, so we have no grand slam metric. And we don't have like a code coverage, so we also have different DNS softwares, and the coverage is different because they have different implementations. By comparing the coverage ratio among the DNS softwares, we cannot get many like useful information. So here we design our ResolverFuzz. So it is a black box, stateful, and a grammar-based fuzzing. So we use 2 inputs, which is from the query and the response side, and we finally grab those outputs and adapt in different oracles to identify different vulnerabilities. So here is our architecture. So for the input, we have a query and a response generator. So we generate a pair of query and response. which means like the transaction ID and other fields will match with each other so that the resolver will not easily refuse them. The second one is outputs. So we have some kind of response cache and system logs, and we also catch the traffic logs via TCP logs. And for the Oracle, we measure the divergence, the discrepancies among those outputs, and we do the vulnerability analysis based on those discrepancies. And for the input generation, we have 2 dimensions. One is for client queries, so this is be sent to the attack clients, and we also have NAM server responses, which is put on NAM servers, so that once a query is triggered, it can send back the responses we want them to send. And also we implement a grammar, which is kind of a structure for the DNS. So we use the CFG, variation of the CFG, which is PCFG, probabilistic time-expiry grammar, to organize the DNS query and response. We also have a response by this small space, so you can check in my paper. So we have a DNS query and response structure with probability assigned to each field based on the frequencies or the extension, the degree of vulnerability for each field by our investigation in the CVE. And also we integrate bi-level mutation. So this is a work in Usenet Security 21, which they found that if we insert some special characters like the slash, like the anti-slash, the @ or the end of the string format, it will, or the dot, or the simple dot, they will just cause like a fragmented or some unexpected behaviors within DNS resolvers. So we add this kind of special characters by using the bi-level mutation after the generation of the payloads of the input generation. So finally we got the ResolverFuzz workflow. So we first initialize all the DNS resolvers, and then we do the test case generation using the query and response. And then during the test case execution, the testing, we will do the data dump with those data I mentioned before. And after we collect all the data, or we have a preset timeouts, 5 seconds when it is done. So we just reset all the resolvers, clients, and the NAM servers for next round. And after we collect all the data, we do the differential analysis. And for the efficiency part, so this is one vital part, because bind is very efficient, but Power DNS, I hope there is no Power DNS guy here. They are not so efficient. I'm not blaming you, but it is a discrepancy, I want to say. So for bind, normally it's like 0.4 seconds, and for Power DNS and another one, Mara DNS, is like more than 1 second. So this causes another, and also different softwares have different ratio of timeouts. So this part like lags down our efficiency. So we just implement a multi-processing, multi-threading programming to increase this kind of testing efficiency. And for the oracles, we have objects with different vulnerabilities. We use different oracles. So we have 3 oracles. So for cache pointing, we have 1 oracle, and this oracle is using the k-means, which in detail is the by-selecting k-means to analyze the groups and clusters. I should use the terms. So use a class to have a cluster. So for each cluster we investigate, and we found whether this kind of cluster is a vulnerability or it's just a very normal discrepancy. And for the resource consumption oracle, we use the filters. So we have several metrics, and we just filter out those ones with unexpected behaviors, or for example, to have too many like payloads or queries between the NAM servers and the resolvers. Normally you should have 1, but you send out 384, it's definitely unacceptable. And also we also, though we didn't focus on crash and corruption oracle, but we did find some crash and corruption and crash on bind 9. So this is kind of surprise we have. And how does ResolverFuzz perform? So we perform our tests on 6 popular DNS software, and 4 popular modes. And we have a good coverage of different fields and values for testing, and it is efficient on our runtime performance. So we test finite, unbound, hard DNS, not technetium, and Mara DNS. So we use Docker-based system to isolate these softwares during testing, and we have schedulers and oracles implemented in Python. And we tested 4 configurations. One is recursive only, another one is forwarder only, and we have some conditional DNS settings, which means like for some of the domains in this picture is the test-cdns.example.com. It serves as a forwarder type, and for other queries, it serves as a recursive resolver. And for this kind of CDNS settings, they also have forwarder only and forwarder fallback. So which means if you have a fallback, if you fail to get a query by the forwarder mode, you just fall back to the normal recursive resolution process and try to get a result. Without fallback is like if you failed to use the forwarder to get a result, that's done. We just we just don't get a result. And here is the evaluation of the each field. So for this bar chart, so it's analysis of how many this kind of fields, these values is shown in with respect to this field. So we find like we have a good coverage of different fields and values, and it is because we use different probabilities for in the CFG. And the test case is prone to trigger errors, and it is potentially bugs. And we found only 17.8 have our code with non-error, which means like we triggered a lot of like malfunction or even bugs during our testing. And for runtime performance, so we achieved 1.9 QPS on CDNs with fallback mode because it is we only test more efficient bind and unbound only because only these 2 softwares they support with fallback. And for rest of the 3 circumstances, we only achieve 2.8 query per second. So because Mara DNS and Tor DNS, sorry about that. And similar speed with real-world DNS resolution. So based on the report of Google DNS, they say like normally in real world it is like 0.3 to 0.4 seconds per query. So it is this QPS. So I think we did good in efficiency. And how many vulnerabilities we discovered? So we find this kind we find 23 vulnerabilities, 19 was confirmed, and 15 CVEs are assigned, and we categorize them into 3 classes. So I want to specially mention about 3 bugs we have identified. One is marginal DNS. So this one is the one I mentioned in the first work. And the next one is Phoenix domain. So it is presented in OARC 39, and it is accepted by NDSS 23. And another one is the first work we just lectured like 30 minutes ago, which is $2 attack, which is accepted by IEEE Security and Privacy this year and presented in this work. And thank you. I'm also, by the way, I'm also open for this summer's internships. If you are interested in taking me up, please consider. Thank you so much. Thank you so much. And yeah, so the NS1 guy from the IBM say I need to have a good presentation today in order to get an internship opportunity or interview opportunity. So for that guy, for that folk, hopefully I did a good job. Thank you so much.
That's hilarious.
Patrick Pacek, I see you. I hope that we will be faster than the IBM guy, because I absolutely love this work. I mean, I'm doing DNS implementations more than, I don't know, a decade or what, and I absolutely love it. We need it yesterday, and I wonder, is any of it public? Like, can someone else run it, or is it either secret or too complicated for anyone except you to run? or what's the state of the machinery for this?
You mean the easiness of using this architecture?
Well, first, is it even public? Is the code you developed for this?
I'm organizing, so there is an artifact evaluation process for Usenix. So I'm now organizing this one. So yeah, it is very easy to run. So it's just run on a like workstation in my lab. So it is not some crazy like you need some kind of like H100 to execute. No, you don't need that. It's just a normal machine. You can just run it.
Okay, so if I understand correctly, you are intending to make it available for other people to run.
Of course,
Is that
I
correct?
will make it public on GitHub. Yeah.
Yeah, excellent. Okay. Anyway, we need to talk.
Thank you.
Thanks. I have a question from the chat. Your QPS seems very low, even for the system you're calling fast. Any analysis of that?
Oh, so yes, thank you for mentioning that. So this is one question like actually the reviewer of the Usenix security asked. So as I say, I don't want to blame someone else, but so because it is very easy to handle the timeouts. So because some of them like binary and bound, they have a low ratio of the timeouts, but you know we are testing like some abnormal behaviors, so timeouts is very hard to deal with. So in order to make things easy, we just brute force set a 5-second timeout. So there are so many timeouts, just as you see, like the normal resolution is about 18%. So timeouts is a little bit too many. And also for those normal resolutions, because of the different efficiencies between those softwares, so it is very hard to do the instrumentation. But this is a very good point. So it is definitely something we can just do further to like do this kind of coordination or between those software to make it more efficient. But I should say the software has the baseline, so that's it. Thank you.
So the further question from Otto, queries being dropped.
Huh?
Queries being dropped.
Dropped? So what? Sorry, which?
That same questioner as extending the question.
Yeah, so if it's timeout, it's dropped. It's just with delivery, delete everything, reset anything, and for next time, for next round of testing. Yeah.
Okay. Thank you.
Thank you.